Welcome back. Now that we know a little more about graphs, we know the fancy terminology around them, let's dive into the nitty-gritty details of actually implementing graphs, storing them or representing them using code. So going back to this image from Wikipedia, it's a graph of a small subset of Wikipedia pages. We have each vertex here is a page or an article on Wikipedia, and each edge, each connection, represents, I believe, a link or a reference, a cross-reference. So if we have this chart here, and somebody asked you to store it using code, how the heck would you go about doing that? What data structures would you use to help you? Would you create your own classes? What would you do? It's not easy, but if we break it down, what we really need to store a graph, the important information, are the nodes, the actual vertices, and then a way of storing the connections. So with a linked list, for example, we did .next and .previous if it was a doubly linked list. With a binary search tree, we had .left and .right in our classes. That's not going to work for a graph really, because there's any number of nodes, any number of edges, connections between a node. So what do? Well, you could come up with any number of solutions. Just like with a linked list, you could store a linked list using an array. It just doesn't really make sense because why not just use an array? Same thing with graphs. You could come up with sort of heavy-handed approaches, but there are two standard approaches that we're going to talk about that most articles, blog posts, Stack Overflow, they're the two common ideas for how to do this. And they are called the adjacency matrix and the adjacency list. So before we dive into that, this is the graph that we're going to work with here. Try and represent this using code. It's a little slimmed down from this one, but it's the same idea. We have vertices, a vertex, and then edges between A and B or A and F, and we need to store that information. So going to the adjacency matrix, a matrix, if you're not familiar with it, is just a two-dimensional structure usually implemented with nested arrays, but not always. And basically we store information in rows and columns. So we could represent the connections here using a matrix, something like this. So the way you would read this, it's sort of a Boolean matrix, yes or no, 0 or 1. So between any two vertices, any two nodes, let's say A and D. So if we look at A and we go over to D, there is no edge. It's a 0, false. There's nothing there. But if we look at A and B, go to A, we look at B, there is a connection there. If we look at A and F, A over to F, where there's a 1 right there, which is how we store true. So this is a way of representing all the edges. Notice that it works the same way if we start here. So if we're looking at the connection between C and D, for example, we could start at C on this left axis and go over to D, and we see there's a connection. Or we could start on C up here at the top and go down to D. And that's because it's an undirected graph, meaning that it's a two-way connection. But we could also store directed graphs where only one way is stored, if that makes sense. So what we have here is a matrix. You could do nested arrays to store this information. Zeros and ones is probably the most common, but you could do true or false. You could do, if you wanted, you could do yes or no. But all that you're storing are the edges. So every time that we add a new node, a new vertex, we have to add an entire new row down here, an entire new column. And we'll compare and contrast the approaches in just a bit, explain what these are good at, what a matrix works well doing, and what it sucks at. Quickly, here's a Wikipedia page. I just wanted to show some diagrams. Here's a representation of an undirected graph here. This is the graph. Here's a matrix storing it. Here is a directed graph. You can see the arrows, and you can see the matrix that we're doing or that we're using is no longer symmetrical.